morning, everybody. It's a pleasure and an honor to introduce our keynote speaker, Hanna Hajishirzi. Hanna is a professor of computer science at the University of Washington and senior director of research at the Allen Institute for AI, where she leads several major efforts to develop open and transparent foundation models. Her research sits at the intersection of natural language processing, generative AI, and machine reasoning, with a long-standing focus on building systems that can understand, reason over, and generate knowledge from complex data. Over the past several years, Hanna has become one of the leading figures in the movement towards open science in AI, and I have been following her work very closely, and I'm really looking forward to her talk. At a time where many frontier models are developed behind closed doors, her group has been building fully open alternatives. She co-leads projects such as Olmo, Tulu, and Olmo, which aim to make every stage of the language model lifecycle accessible to the research community. These efforts go well beyond releasing model weights. They include open data sets, training pipelines, intermediate checkpoints, evaluation tools, and detailed documentation of the entire development process. By doing this, Hanna and her collaborators are helping transform foundation models from proprietary artifacts into scientific objects that can be studied, reproduced, and improved by the broader community. Her work also speaks to a broader policy question about the future of AI research and infrastructure. Efforts like Olmo demonstrate what it means to build open, transparent, and reproducible AI systems that can serve the scientific community. And in that sense, Hanna's work is not only advancing the state of the art in language models, but also helping define what public AI infrastructure might look like. Her work also spans a wide range of topics central to modern AI, including reasoning in language models, multimodal learning, knowledge extraction from scientific literature, and rigorous evaluation of model capabilities. Many of her projects tackle questions that are increasingly important for trustworthy and responsible AI, such as tracing model outputs back to training data, detecting hallucinations, and developing better benchmarks for model behavior. Hanna's contributions are widely recognized. She is a fellow of the Association for Computational Linguistics, a Sloan Research Fellow, and a recipient of the NSF CAREER Award. She's also received the Allen Distinguished Investigator Award and the Torode Family Career Development Professorship, among others. Her work has received best paper recognitions at leading venues such as ACL, CVPR, and AKBC. And the Olmo project was recognized with GeekWire's Innovation of the Year Award. In addition to her research, Hanna has been an exceptional mentor. Many of her former students and postdocs are now faculty members at institutions like Carnegie Mellon, UC Berkeley, and UT Austin, helping shape the next generation of AI research. And today she will speak about Olmo 3, the newest generation of open language models developed by her team, and introduce the concept of model flows, a framework that opens the entire life cycle of model development to scientific investigation and customization. Please join me in welcoming Hanna.
Thank you very much, Julia, for an amazing introduction. So I'm very honored to be here to present our most recent work on open language modeling efforts. Okay, so before that, let me give you a very quick overview of my journey through AI. So I started my first project in AI on doing symbolic reasoning, kind of approaching it old school AI on how to address reasoning problems just with using logical filtering. My first work in NLP was how to solve arithmetic word problems. Like, look at the type of problems that our models were able to solve back then. It was one of the first papers on how to solve math word problems. So then I moved more toward more general purpose question answering from and reading comprehension questions from textual paragraphs. and then making it more general purpose by developing a unified question answering system. And nowadays, our systems, like this is a question I asked our Olmo 3 demo on how to solve more math competition type problem. So I provided this overview because I thought this is also very much aligned with how the field of AI is progressing over time in such a short period of time. But the difference between the first types of problems we were solving at EMNLP 2014 till the type of problems that our models are solving, like frontier models are even doing more complex reasoning tasks, is like really huge difference. Okay, so as we've seen, AI is everywhere these days. Okay, but there are still many problems that haven't been solved. Usually when we interact with different AI systems or AI models that are available, it's just their final snapshots, right? Either APIs or the weights that have been released and we are using in our model development. I want to argue that AI models are not just the final snapshot of this long process of how they have been curated. And here at AI2 and my team at University of Washington, we argue that it's really important to have access to the whole model flow or the whole development cycle of model development. Why is it important? Because it helps and enables researchers and developers to customize models across different stages of training of the models. So not just a final snapshot, but maybe intermediate steps are more important for some use cases. So Julia mentioned this. The Olmo project actually is a collection of artifacts that we are releasing. It includes all the weights of the final model, the training and the training and inference code and procedure, all the data across all different stages of training, all the evaluation suites, like how we reproduce it, what prompts did we use, the technical report of how we have developed these, and everything is reproducible. Besides that, we are releasing all the checkpoints, like even the checkpoints that we have achieved during training, the variance of the data set, and also how one could curate data for their own purposes by releasing the tooling that is important for data processing. Okay. So a quick kind of story and history of different models that we've developed. So we started this project roughly around 2022, where our most focus back then was on demystifying post-training in building language models. So we first looked at this project called Self-Instruct, where we argued that we can generate synthetic data from the output of language models and then show how we could use it to improve the models themselves. So this project got a lot of attention, and around that time, I was actually got contacted and learned about the NAIR program and wrote a proposal to get more resources to generate more synthetic data. And with that, we managed to build this next artifact. We call that Tulu, which every model back then was built on one of the llama-based models, and kind of Tulu was the bigger camel. That's why we named it Tulu, where the idea was it's just a post-training process. We used a collection of synthetic and manually curated data, and we showed how we could improve language models. And back then, there were a lot of arguments that was around the time that GPT-3 and ChatGPT were available, and it was around the time that these open models could also compete and show on benchmarks that they are very close to some of the closed models. So we started improving the post-training process, arguing that not supervised fine-tuning alone is enough, and we need to do preference tuning and introduced Hulu2, we kind of studied different algorithms on how preference tuning should be done and introduced Hulu 2.5. And then finally in Hulu 3, which we released last year, we introduced this concept of RLVR, which probably some of you would know. It's reinforcement learning with verifiable rewards. And around the exact same time, DeepSeek came. And kind of a lot of people in 2024 started thinking that, OK, reinforcement learning is important, and we need to kind of do this type of verification. In our Olmo project, we started this effort on demystifying pre-training. So obviously, this is much harder because it requires a lot more resources. Again, we were lucky enough to get some resources from different partners, including NAIR as well. And we started the first Olmo project in 2023, which now, when I think about it, I would mostly call it proof of concept. We made a lot of mistakes in that process, but it was an interesting effort to showcase that we are able to release everything about the model, including the data, including the training recipes, and show how pre-training can be done. So we started, we continued this project, improved it, and released Olmo 2 and Olmo 3, which was released in December last year. And I'm going to talk about the details of Olmo 3. So just before that, I want to showcase that this has been useful, I believe, to the community. This is developed mostly by researchers from our team and my students. And a lot of people in the research community keep using it. So some of the use cases have been to study how different behaviors of training are acquired during pre-training, how these type of open source models shape policies, and also what are the behaviors that we could expect during post-training once we have all these checkpoints. We are also getting some letters and kind of testimonials of how different groups are using our models in their process. We've been very happy to see that this is one of the most open kind of artifacts that have been released by our team. People are using our artifacts. These numbers actually were very surprising to me because we are researchers. I honestly didn't expect to see these many downloads. But since 2023, we've had more than 32 million downloads of our artifacts. And yeah, this is kind of giving some numbers about how people are using our model. So in 2025, probably like last year, you saw a lot of groups are working on reasoning models with various definitions of what reasoning means, okay? But now, what do we expect to be happening in 2026? And if you think about it, these days, at least all of my students are basically supervising coding agents rather than writing codes themselves. So I think a lot of people are like this. So I would argue 2026 is basically the year that agents would change how we work. And I would expect to see a lot of agentic work in the open domain as well. Again, a little bit of kind of description. So these days, a language model consists of these three parts, which is the model weights, the tools that the model is kind of aware of, and a harness on how these tools will be used, okay? The closed models like GPT, Claude, Gemini, and so on are the full package, okay? So they are coming with the harness. They have full control of the tools, the experience, and also they could generalize to different platforms. So open weight models are still not there, and they are making progress in that aspect. So in Olmo 3, this is a 2025 release. That's basically, we are working on this part, which is weights plus tools. So our model, we are releasing the weights of the model, and also the model has knowledge about some tools that we introduced during training. So we hope that we can work with the community, with all the researchers, to improve this part as well, which is how to build different platforms, harnesses, environments for interactions for different open models. Okay. So this is a quick snapshot of what we've done in Olmo 3. So I keep mentioning model flow, which is the whole training pipeline and the full development cycle of the model of Olmo 3. And it consists of these like roughly 6 stages: pre-training, mid-training, long context extension, and different stages for post-training. And at the end, we curated these 3 artifacts: Olmo 3 Thinking, which I'm going to talk about today; Olmo 3 Instruct, which is a model that kind of is mostly useful for chat and tool use; and then finally, Olmo 3 RL0, which is a research artifact that is just applied reinforcement learning at the end of the base training model, which has become very interesting to researchers to understand model behaviors and of like, do we have this aha moment, or like, what does it mean that a model can reason? So it's mostly a research artifact, and it's interesting. I encourage you, if you are excited about reasoning, this is a good kind of model to play with. Okay, so again, I had to show these numbers that at the end, the results look great. So Olmo 3 is the best fully open across the benchmarks that we are evaluating, and it is getting on par with other open weight models. For example, at 32B scale, it's almost similar to Quen 32B models. We released this model right before Thanksgiving last year, and so far we've seen more than 3.8 million downloads of the model across the model checkpoints and also the data sets. And again, it's very interesting, and we were kind of expecting it, that a lot of downloads are actually from the data sets that we are releasing, with the argument that data plays a very important role, but most other model developers don't share the data. Okay, so now let's dig in on how this model development looked like for Olmo 3. So I'm going to talk about these 6 stages and then go a little bit deeper into each of these stages. So in the base training, it's like pre-training, mid-training, and a long context extension, and the post-training, supervised fine-tuning, preference tuning, and reinforcement learning. So at each of these stages, I want to also mention this point that it's really important to have this cycle of evaluation, data curation, training a model, and very careful evaluation. And since this process is iterative, and then we need to keep improving it, given better and better evaluations, we learn how to update our data on our model. So this is actually a really important cycle that we will be updating through our model development. Okay, so this is also some of the principles that we learned throughout the model training, which is this whole process is iterative. And it requires to have a good balance between these 4 elements, which is innovation and execution balance. We need to have, basically we had our students and our team members to go off the rail, do some explorations on their own, and they had a few months of making that progress. But then after that, we started making sure that we are at the execution phase, where we put all of these together, and with heavy engineering, we need to kind of combine and integrate all these efforts. But how is this possible is through improvements on the infrastructure, which was very critical, because with without a good infrastructure, we're going to waste a lot of resources. And it's very important to have high quality infrastructure. And also operations to define, share the standards on model development to see how these things can compare with each other once we are kind of deciding what types of model features to keep and what types they are contradicting or conflicting with other capabilities. And throughout this whole process, this was also one of our important principles. We are all researchers, so we made sure every step is scientific. We could justify our decisions and make sure others are able to reproduce the results. OK, so during pre-training, let's talk about the first stage. Again, I want to highlight this is a cycle. This is an iterative process. We focus on scientific methodology. And we are still kind of working in poor GPU setting. So we make sure that we optimize quality versus cost. Okay, so whatever we could, we want to kind of optimize for the cost. So for that reason, we are talking about these three important kind of changes and decisions that we needed to make. One, before the pre-training run. Two, during the pre-training run. And then have better and better and higher quality data. OK. So before our pre-training run, we invested a lot on having good evaluation metrics. OK? So as the model progresses, we want to look at more and more capabilities that we like to add to the model, okay? And there are a lot of academic benchmarks that are available that evaluate these capabilities. So we looked at a really large collection of these benchmarks, like more than 100 or so. And then we started checking which of those are giving us good signals for training, okay? And then, in order to make features or kind of decide what type of data to pick or what type of model architectures work better, we needed to see that these capabilities are getting acquired, but only with very small cost, right? So for that, we need to build good scaling laws. Some benchmarks, let's say Arc Challenge, okay, are very informative. So as you see on the left, as the model progresses, the performance gets higher and higher. Okay, so this is good. Like even at very small scale, we started seeing some signals. But then now for Olmo 3, we would like to improve math reasoning capabilities, but at very small scale, even like less than 1 billion parameter, which is where most of our ablations did happen. We didn't see any signal on a data set like math, okay? Which was not that informative, and it was very hard for us to see progress. Like, when we add this data, do we actually see improvement on math capabilities? And so this was a very hard challenge for us. So over the time, we learned how to improve metrics, right? So we came up with proxy metrics on how to see math progress over time. And also, we started developing some synthetic data sets on evaluating very simple arithmetic capabilities during the model development. So these were kind of some of the important steps that we needed to take before pre-training run, and you could check our repos for those. During pre-training, we made progress in different fronts. One, we have to make sure our training is very stable. So I don't have any example here, but over the time, we saw that when training is unstable, meaning that the loss is not smoothly decreasing, something is wrong, either with the data or model architecture, and we need to keep improving, and that hinders model progress. We need to improve training infrastructure, meaning that get as many, make sure GPUs are not wasted, try to have better and better throughput during training, okay? So we started with like very small number of token per second for training to almost 13,000 tokens per second for training our 7 billion parameter model. Also, as you would expect, model architecture also matters in having good models. Okay, so for that, I want to talk just for 3-4 slides on why model architecture matters. So in our very latest release, Olmo Hybrid, which we actually released last week, we argued that, kind of in theory, that it's a good idea to combine transformer models with linear RNNs. Okay, so I'm not going to go into the details here, but probably you've seen in the most recent releases in the other open models like Qwen 3.5 and Nemotron releases that they are also using hybrid models. So we were actually motivated by theory why hybrid models are good. So one of our very amazing postdocs came up with this kind of theory that transformer architectures are great in recalling knowledge, but they are not good in representing and expressing tasks that require state tracking, okay? On the other hand, linear RNN architectures are really good in state tracking. This is like the nature of RNNs, but they are not good at recall. Okay. Hybrid models can take the best of both worlds, like you see the intersection, okay? And it's better than both of those models. So they could express more models. Okay, so this is a good intuition that, okay, we can think of an architecture that represents more and more problem. Okay, so for that, we decided, let's train a model. Let's see how it works out in practice. It was very surprising to us, honestly, that, for example, look at this curve. This shows how MMLU, shows MMLU accuracy throughout the model training. Okay? So honestly, I was pleasantly surprised to see that we got to the same accuracy for MMLU with only 49% of the tokens. Okay? We also did our scaling laws, compared, oh, I don't have the legend. So the dark blue is linear alone. The pink is the hybrid model, okay? And this is loss, so the lower the better. And as you see, the hybrid model, kind of its lowest, it has lowest loss on our validation set. And again, this shows that the hybrid models is empirically much better than the other two. Still, this is surprising to me. So we bought this argument that the hybrid models are more expressive, okay? But the type of evaluation tasks that we are evaluating, I didn't expect to see, why are we acquiring these accuracies much faster than expected. So we started doing more analysis and then kind of do more theory of understanding why is this happening. Okay, so this is the open question. Has a better, when hybrid models have better expressive power, does it mean that they also have better scaling behavior? So basically, in theory, we could explain it with the quantization model that were presented last year. Okay, so I'm not going to go into the details. We have a couple of theorems in the paper, in the technical report, but the gist of it is this. If we assume a probability distribution over the space of tasks that are expressible, the more expressible the task is, the loss drops more quickly. Okay? So look at this curve. So a lower epsilon means that the task is less expressible. Okay? And as you see, with the higher epsilon, the model converges faster. Okay? And that was a very interesting observation. And over the time, we saw that this means that the hybrid models are more data efficient for scaling. Okay. So now the final component, data, which I would argue data is key. All these components are important, but at the end of the day, the capabilities that the model has is due to the data that you are using to train a model. So once we want to have a large collection of capabilities for the model, we need to mix the data, okay? So the dark green curve shows the data mix that we used for training Olmo 2, where we were less focused on reasoning capabilities. But then for Olmo 3, since we want to add more reasoning capabilities, we kind of learned what is the best and ideal data mix for that. Okay? And now you see these pink bars where we learned that this is, again, diverse, but it steers heavily toward the STEM and science type text. Okay? Like, for example, in Olmo 2, 95% of our data was common crawl, which was kind of web data, and now it's only 75% of our data is common crawl. So how did we build that? Again, I'm not going to go into the details, but here is the gist of it, which is we defined a mixed constraint token budget. Okay, we said we're going to train our model to 6 trillion tokens. I know other teams train longer. We are obviously limited by compute. So we set our data constraint to 6 trillion tokens. And then we kind of calculated how many tokens from each of these domains we should be adding to model development. So how did we do it? We built a regression model. So we trained these swarms, which are much smaller scale training, on random mix of the data. Okay, we brought some prior, like from natural distribution, and also many different types of mixes. Okay, so this stage is cheap, right? Because we are training super small scale models, like in the order of 20 million parameter models. And then we kind of fit this regression model. So all those dots are those smaller scale models that are trained. And then the line shows what is the kind of how the regression would look like. Okay? And then we solve this optimization problem, which is give me the best mix such that my metric, that evaluation metric that I am tracking has the best number or has the best value. Okay? Good. So this is my data mixing. But at the end of the day, once we want to have reasoning capabilities, it's really important to add a long context capability. Like obviously, we know all closed models have better and keep getting better and better in long context training. But there is a big challenge in long context training, which is most of the data that we can find naturally are a very small scale, like in the order of less than 4,000 tokens. And it's much harder to actually, like you can concatenate that data to make it to long context, but it's more like artificial. So we thought where we can find a long context data, and obviously scientific papers, which are really good source of high quality data. But most of scientific papers are in PDFs, okay? So we need to find a way to linearize them, make them usable for pre-training. So how do we do that? First try, we're going to use one of the closed models, in our case GPT-4, to linearize these documents. But it's going to be very expensive to use GPT-4 for this kind of as OCR processor. So for that purpose, we needed to build this tool, which is actually one of our most useful downloads these days. It's called Olmo CR. We trained a model to actually build an OCR representative. Okay, so how to linearize, basically we are using a vision language model on how to linearize PDFs into tokens. But at the end of the day, we managed to curate about 10 trillion tokens of long context data at 1/30 of cost of using GPT-4. On the side, we've also curated this benchmark for OCR in order to evaluate the OCR capabilities. And now you are seeing a lot different OCR models in the open as well. OK. So now let me move on to the post-training stage. So it starts with supervised fine-tuning, preference tuning, and reinforcement learning. So let me give a quick summary on supervised fine-tuning stage. So we included available curated data that we could find, and also we created a lot of synthetic data at this stage, for example, to address math problem solving, and so on. And again, I want to highlight NAIR resources here that we got a lot of NAIR resources, particularly from Microsoft Azure, which enabled us to curate lots and lots of synthetic data for SFD, a very useful resource for us here to bootstrap reasoning for the post-training stage. Similarly, we used, again, similar credits for preference data to show that how we can, for a prompt, what is the chosen response, what is the rejected prompt, and then we use and then the last stage is reinforcement learning with verifiable reward, which I'm gonna go into more details here. Okay, a quick recap of what I mean by RLVR. So we've seen and we've heard that reinforcement learning is very useful when we want to build reasoning models, but this is kind of how it works. A prompt comes in, the model policy keeps getting updated, it updates a response, and then like in the traditional RL, you want to update an environment and then keeps getting feedback. Okay. What is RLVR? That environment is super simple. It's just a verifier, okay? If you solved a problem correctly and you could verify it, 1, otherwise 0. Okay, so this is kind of the very simple idea. So we introduced this in Toulouse 3, and we saw that in types of reasoning tasks that we were looking for, we are seeing good performances. For Olmo 3, we actually make it much more diverse. We now have verification defined for instruction following tasks, for code generation, mathematical reasoning, and general chat. And we kind of kept a good balance of all of them together. But now, a lot of this data has long context. And reinforcement learning on long context is actually very challenging and very expensive, okay? But let's discuss why. The reason is we have 2 sets of GPUs and 2 sets of kind of compute going on, working with each other. One is generation GPUs, and also verification and training GPUs. Okay, let's get into the details here. Generation GPUs is, for a given prompt, you want to generate multiple responses. Okay, so this is where you call your inference. Then these sets of GPUs stay idle for some time. The CPUs come into play, they start verifying if these are good or not, and then training step happens, okay? Now, these new GPUs will be staying idle, and then the generation GPUs come in, okay? And then this cycle repeats. Okay, a lot of waste of GPUs, so obviously this is not a good strategy here. This even gets worse when we have long sequences, right? So in the generation stages, let's say we have a mixed batch consisting of all the types of data that I showed you, but then now we are looking at a complex math problem or a complex coding question. So the stage that the idle GPUs stay for training, it's even longer. Okay, so how do we solve this problem? Is something like this, that we are okay that our policy updates are not on policy, okay? So we constantly, our inference GPUs constantly generate, and we do active refilling, okay? And then at some stages in the training, we collect whatever data that has been generated, pass it to the training stage, okay? And if we've got stuck into one of those long generations, we update our KV cache, and in the next stage, again, start adding to it, okay? So what is the side effect? We are a little bit off policy, right? So for some of the longer generations, the model is getting updated, but that generation hasn't finished. But it is okay. In practice, we didn't see any difference. I'm not going to go into the details, but the final Olmo RL procedure is a variant of GRPO, the popular reinforcement learning algorithm that is going on these days with some changes. Please check the technical report for the details. But here are our results. So as I said, with all these changes that we've done, here is how we made progress. In some of our earlier RL runs, progress was so slow that we couldn't see much progress. And probably you heard last year that we are doing our RL, we don't see any gains, or we are doing our RL, something very, like in some domains we see gains, other domains we don't see gains. Same for us, because RL signals usually come later, especially for some domains. And the reason was exactly some issues with our infra, and also all these on-policy training. With all the changes that I mentioned, now you see these pink graphs that we get almost 5 times improvement in how early we could start seeing our signals during the RL training. Okay, so this is also a very interesting observation that we released our Olmo 3 around, like right before Thanksgiving. The people all disappeared. We just didn't stop our RL training. We just let it train longer just because we had some GPUs available. People were tired. They were not working on new things. And over time, after about 2-3 weeks, so look at, so at the beginning of the graph is what we released, and then the final kind of pink stars are how much better the model got just by sitting and doing more RL training, which was very interesting that in a lot of benchmarks, particularly the ones that required more reasoning, RL showed even more improvement when we let it train longer. Again, this is a quick snapshot of the final model, which compare the pink are the Olmo 3, and all these are different models, open weight models, and we show how we could get similar accuracies, particularly to Quen 3, which was the best open weight model back then. Okay, so I want to also talk about one more topic, which is I chatted a lot about RLVR with verifiable rewards, okay? But in all those cases and tasks that we were working, we assumed we could verify the final answer, okay? But now the big question is, does RLVR work for when we are looking at open-ended, long-form, unverifiable tasks, okay? And basically for that, we were in parallel working on building a deep research agent on top of our models. So let me define what I mean. So let's say I have a question, like what is the differences between Olmo 2 and Olmo 3? So basically, we want to search and find what are Olmo 2, what are Olmo 3. We kind of come up with a plan. Like you've used all these deep research agents these days. But the point is the final answer is this long generated text that compares the differences between these two, okay? And it is not easily verifiable, right? How do I know what is the correct answer, what is the wrong answer? What we want is being able to make sure attributions are correct, right? If there is citations to like some work, make sure there are no hallucinations. Also make sure it is up to date. Like there are some factors that we need, like as a researcher, we would consider to see if the generated answer is correct or not, okay? And basically we define, and also people in the community are using it, which is we need to use rubrics, right? Rubrics are these kind of features that we use for evaluating the final answer. So the key idea in our Dr. Tulu work was to introduce this new way of doing reinforcement learning with evolving rubrics. Okay, so we all agreed that rubrics are important. So we started with, okay, let's define, we talked to some experts in computer science and in computational biology, and we came up with these rubrics that were useful for evaluating these final answers, okay? And then we said, okay, that's good. I'm gonna, instead of doing RLVR, which is just a simple verification, we would use some sort of weighted linear sum over what the value of those rubrics are, okay? So we thought this is a good strategy, let's do it that way. But unfortunately, it didn't work out. Why? So we soon realized that these static rubrics are not the solution here because the models keep to learn to hack these rubrics very quickly, okay? So some generations happened, they were satisfying those rubrics, because those rubrics are not perfect, right? The ones that we can initially come up with. But the final generation didn't look good. So over time, we learned that we need to update our rubrics while the policy improves, okay? And this is our final solution. So throughout the training, we keep updating our policy. But now, remember in RLVR or in any reinforcement learning algorithm, we generate multiple responses, okay? And over time, we keep updating these rubrics by saying that now some responses should be boosted and some responses should be kind of penalized. And this is the essence of how these rubrics would evolve over time. So this is kind of the very quick cartoon of how it works. With initial rubrics, we generate some responses. We do our search, okay? And then we generate these different policy rollouts. We evaluate it according to this kind of a featureizing stage that I mentioned. But then we start updating it. We have a buffer of rubrics, and then we keep removing and adding new things. And this process continues. OK, so some results. This is the pink is our model. And comparing to other deep research agents, which were mostly designed for short queries, for short responses. Obviously, the model is better. Honestly, it wasn't that much of a fair comparison. But then we compared with some of the closed models, like OpenAI Deep Research, Gemini Pro, that just came out almost the same, I think exact same day that we released Dr. Tulu. And our model is better compared to those on the benchmarks that we are evaluating. That was very interesting and surprising to us. And again, this is how the score, like this kind of compares the score of the model on our benchmarks versus the cost. And as you see, Dr. Tulu is significantly cheaper compared to some of the closed models. And this showcases the fact that we could build the specialized models for the tasks that we care about, and they are better than the closed alternatives. OK, so I'm almost out of time, and I'm kind of wrapping up here. But I want to highlight a few important things. So this is the whole pipeline. I talked about different pipeline, the pipeline we use in building Olmo 3. But this is kind of the big discussion I would like to also point at. So what guides our development, or not just our development, every team's development in building foundation model? Evaluations and the metrics. And I would like to call it imperfect evaluations. So every team that they say our model is best, so I try to make sure to say we get good numbers compared to Quen on the benchmarks that we are evaluating. So everyone is optimizing and maximizing on their evaluation suites. And everyone says our models are best, again, on our own evaluation suites. But yeah, this is important. So all models have different strengths and capabilities and weaknesses. And if we just report an average number, it's kind of meaningless. So it's really important to kind of be aware of what type of evaluation metrics different models are reporting. So over time, we've done a lot of analysis over the academic benchmarks that are available. Some of these benchmarks have really high variance, and over time we learned like we shouldn't care much about them at some point, and don't make our final kind of decisions based on the values on those benchmarks. So I'm listing some of them. You've probably heard some of these names, and some of them are very stable. Like, for example, math benchmark, MMLU benchmark, they are actually very stable. One reason for them being stable is like they have a lot more instances, actually. Also, some of these evaluation sets, some of them are easy to hill climb. Some of them are not that easy to hill climb. So over time, for example, we learned that the knowledge benchmarks like GPQA, MMLU, and so on, most of their gain is happening during the pre-training. And whatever we do at post-training, we are not gaining much more, okay? However, some benchmarks, like reasoning benchmark, most of the gains are happening throughout the post-training. Our team used a lot of our, at least 20, this is, the title is cut out. So at least 20% of our total GPU usage was used on evaluation, okay? So obviously we know our evaluation infra was not that perfect last year. We are improving, so we are doing a lot more parallelization and so on to improve our infra, but 20% is a lot, right? Compared to, I personally was shocked of seeing that over the time we use 20% of our GPU on evaluation. Also, we spent 20% of post-training time on GPUs. Like our model, everything was ready. In the last 2 days, we were just constantly evaluating to make sure that we are reporting all the numbers. So at the same time, we need more and more evals because we know how to hill climb and improve these evaluations to add more and more capabilities. Like basically, I think we consume almost all of the academic benchmarks that we could during the pre-training process. We also generated and built some synthetic evaluation, but I really want help from the community to build more and more evaluation sets to kind of increase the capabilities. So what do we need? Again, we need to make evaluation more efficient, okay? And we need more evaluation. And this is kind of an important cycle that we need to have to make more improvement. So what do we need to improve our current open foundation models? Data, scale. These are two important steps. Olmo is a representative of how the fully open language models look like. We know how to hill climb and improve our benchmarks. We know if we want this capability, there should be an evaluation metric, and we need to improve upon that. So we need help from the community on how to make progress there. And in general, there are still many problems that haven't been addressed or haven't been solved. This is like even the frontier research. Reasoning and agents, obviously, we're going to see a lot of progress this year on both fronts. We need to rethink the data paradigm, which is these days when we train a model, we assume that data is binary. Either it exists, it's like public data, or it's private data and we cannot train on that. So how can we smoothly go between public-private data training and then kind of have some options for opt-out if there is some data during pre-training, but we want to opt out. We need to look at and bring in all our kind of progress in AI to other domains, like education. I think this is a super important domain, science, and so on. And we are seeing a lot of research this year for AI, for science type of work. And finally, efficiency and personalization. Again, agents are everywhere these days, but we do not like these models work with our private data. So we need local models on our laptop, on our cell phone. So working on efficiency and personalization is a super important topic. Okay, and at the end, I would like to thank all my students, my team, my Olmo team, and all the collaborators from other universities and other institutes. And thank you very much for having me here.
Thank you so much, Hanna. And I think maybe we have time for one quick question while I invite the panel to come to the stage. Yeah.